explore an exciting concept in physics, wave production, focusing on longitudinal waves using something simple yet fascinating, a slinky. Waves are all around us, from the sound we hear to earthquakes and even the vibrations inside musical instruments. But not all waves move the same way. There are transverse waves, where particles move up and down, and longitudinal waves where particles move back and forth in the same direction as the wave. In this activity, I'll show you how to produce a longitudinal wave, explain how it travels, and connect it to real-world examples like sound waves. Let's start with the concept. A longitudinal wave is a type of mechanical wave where particles of the medium vibrate parallel to the direction of the wave's motion. If we imagine a row of tiny balls connected by springs, pushing one ball forward will compress the others. That's called a compression. And when it returns, it leaves a rarefaction, an area where the particles are further apart. So, longitudinal wave is basically a pattern of compressions and rarefactions traveling through a medium, just like how sound travels through air. You can think of it like this. When you speak, your vocal cords push air molecules, which then push other air molecules, transferring energy forward, not the molecules themselves. That's how sound reaches your ears. So here's my setup. I've stretched a slinky across this smooth surface. The coils represent particles in the medium, like air molecules in sound. Now, I'll hold one end steady and give the other end a small push forward. Then pull it back to the starting position. See that? The coils move closer together. That's a compression. And when they spread apart, that's a rarefaction. The pattern moves down the slinky, even though the coils themselves only move back and forth. This motion shows how energy is transferred in a longitudinal wave. Now, if I do this repeatedly, you'll notice a series of compressions traveling down the slinky. Increasing the speed of my pushes changes the frequency, and the strength of each push changes the amplitude. So, this simple setup perfectly demonstrates how sound waves travel through air, not by the air moving to your ears, but by compressions moving through the air. So what does this tell us? This experiment with the slinky shows that wave transfers energy and not matter. The coils move back and forth, but they don't travel across the table, just like how sound travels without the air itself moving from the speaker to your ear. A real-life example of this is sound waves, the vibrations of a guitar string or your own voice. The compressions and rarefactions in air molecules allow us to hear. Another example is seismic P waves. These are longitudinal waves that travel through Earth during an earthquake, moving faster than other wave types. Many students think that the particles travel with the wave, but as we saw, they just vibrate in place. It's the energy that moves forward. Through this simple slinky demo, we can see and can even feel the invisible push of a longitudinal wave. And that's the power of simple science. Thank you for watching, and I hope you now see waves not just as lines on paper, but as living, moving patterns of energy all around us.